We're moving from Ethernet technology now into the specific implementation of Ethernet in our networks today, LAN switches. So we're going to take a moment, just a brief moment, to understand LAN switches and see what they're all about. We'll start off by looking at the problem of CSMA-CD. That's Carrier Sense Multiple Access Collision Detection. We talked about that in the previous video. So if you don't remember what that is, you might just glance back at the previous video before we get into the LAN switching world. We'll then look at collision domains and broadcast domains, what the difference between them are, what their relevance is to our LAN switching world, and why LAN switches implements them so much better than the old days, which is hubs. We'll then wrap up by taking a look with what switches do, essentially how a switch switches. Well, let's start off by talking about the problem with shared CSMA-CD communication. Now, you may remember CSMA-CD is the rules of engagement for Ethernet. They're the rules that govern how devices talk. And when we first got into the Ethernet world until the probably I would say late 90s, just about everybody was using this device known as a hub. And hubs and switches perform the same function in that they connect all the devices to a network, but there's a world of difference between them. As a matter of fact, I was actually standing, this was probably a couple of years ago now, at a store that shall remain nameless. But the employees wear blue shirts with yellow name tags. And I was standing in this store like I do all technology stores. I kind of just gravitate to the technology networking area. I'm not really much of a music guy. I don't get into the TVs and all that kind of stuff, but just the networking stuff. And I was just standing in the networking aisle looking at some network cards and some webcams and stuff like that. And I saw this guy down the aisle, and he was just kind of looking at sale. I don't know if you've heard of the brand name of Hawking, but they make some really low-end switches and hubs and things like that. And I was sitting there looking at him out of the corner of my eye because a blue-shirted employee had walked up and had said, "Well, is there anything I can help you with?" And he said, "Well, yeah. I saw that you had a sale on these Hawking 8-port hubs, and they're $9.99, and right next to it, they have a Hawking 8-port switch for $39.99." And he goes, what's the difference between them? And the blue-shirted individual picked up the two boxes and was looking at the stats on the side. And by this point, my interest is kind of peaked. I'm like, oh, I wonder what he's gonna say. And he finally turns back around. He goes, well, I'll tell you what. This switch here is kind of the new model. It's got kind of the chrome plating cover, and they're trying to phase out this old design of the hub. I'm like, having a heart attack in the middle of the aisle, and the guy was like, "Oh, okay, well, I'll take the $9 one if they're just discontinuing it because it doesn't have chrome on it." And I was, "Oh no!" There's so much difference between a hub and a switch because in the day everybody used hubs, and for some instances hubs are still appropriate and can work okay, but when the hubs were mainstream, what they do is just regenerate signals. When this computer sends a message into the hub, it may just be wanting to communicate to this computer, but everybody gets it. Remember we talked about the types of network communication was unicast, multicast, and broadcast? Well, in a hub, it doesn't matter. It doesn't matter what kind of communication you're using. Unicast, broadcast, multicast, it treats them all the same way. When a message comes in from a PC, it just goes out to everybody. Now, this hub is said to have one collision domain. This is one of the objectives that I was mentioning. One collision domain. What is a collision domain? Well, there's a lot of super technical definitions for it, but I'll boil it down to how many devices can send or receive at the same time. And in a hub, it doesn't matter how many ports you have, the answer is always one. There's only one collision domain. Likewise, let me define that other term that was on the introductory slide. Broadcast domain. It's very difficult to talk and write at the same time. One broadcast domain. A broadcast domain defines how far a broadcast will travel before it stops. In a hub, that's also only one, meaning one broadcast will travel everywhere. It goes out all ports, completely saturating the network before it's finally stopped. It doesn't matter if I have a hub linked to a hub using a crossover cable, and that goes to another hub with a crossover cable. It is always one collision domain and one broadcast domain. Only one device can send or receive at a time, and one broadcast will travel everywhere throughout that network before it ends up stopping. This is the problem with shared CSMA CD communication, is remember the rules of engagement here. When you plug these devices into a hub, the carrier sense says that they will listen before they transmit. And if nobody else is using the wire, then they'll both try and transmit that. Oh, I'm stepping on my wire. Sorry about that, my headset here. That if they both try and transmit at the same time, you're going to have a collision. Now, when you add more and more computers to this network and more devices attach in, somewhere around 20 to 30 computers in this hub network will start causing a problem. The problem is more than one device is listening at the same time, meaning, remember, they just listen to see if somebody's using it. The more devices you have, the more chance you have of more than one device listening at the same time. And if they're both listening and it's both silent, they'll both send their message at the same time to the hub, and you will have a collision. Now, here's what happens when a collision happens. Usually on a hub, there's a little light right here, and it'll blink. You'll see a little blink. Collision just happened. And what happens when that occurs is one of the devices that detected the signal will send out the signal known as a jam. What the jam does is it says, hey, everybody, I just detected a collision. I am going to stop all network communication for a moment because we need to resend our data. This device and this device, after they've received the jam signal, everybody stops sending at this point, will wait a random timer interval. Now, it's in our terms, it's a very quick timer. It's in the range of 1 to 100 or 1,000 milliseconds. So within less than a second, they've resolved it. They've both sent their signal. The jam is now released, and everybody can start sending using the normal CSMA CD communication that we're all used to. But again, the more devices we have on here, the more chances that'll happen again and again and again. I've been in networks where I've seen hubs and the collision light is almost solid, meaning there's so many devices that are having collisions that it's just happening again and again and again and again. And what happens to your overall network communication is it just slows down because everybody has to stop, everybody has to wait while they resend their data, and then communications happen again. Oh, collision happened, everybody stops, everybody waits. So the overall feel is that the network is much slower. Now, as technology was beginning to advance, when we had just hubs, this device known as a bridge, some people called it a transparent bridge, but a bridge came out into the network. Now, what the function of this bridge was to learn MAC addresses, and it would learn all of the MAC addresses on one side of the network. You can see over here I've got one group of MAC addresses. I've got 2 PCs, but imagine that to represent 20 or 30. And they're all plugged into their hub. And the bridge learns everybody's MAC address on that side of the network and everybody's MAC address on this side of the network. By setting up a bridge in this device, in this environment, I've effectively split my network into 2 collision domains, meaning I've got one collision domain over here and one collision domain over here. The bridge learns all the MAC addresses that are on this side of the network and this side of the network, and also allows one computer to be sending on this side at the same time as one computer can be sending at this side. Now, the cool thing is as this bridge becomes smarter and learns the MAC addresses on the network, let me just clear off all my scribble here, it will become intelligent. As in, it will be able to say, when a computer comes in and says, I would like to send to the MAC address 00AA, some MAC address, which may be located right here. Of course, on this side of the network, everybody gets that message saying, I would like to communicate to that MAC address. It comes to this bridge and it goes, oh, you're sending to that side of the network. So it comes out to this hub. What does the hub do? Send it everywhere. And everybody, including this one, gets it. Now, what if this computer was sending to a MAC address on this side of the network? Like maybe this MAC address belonged to this PC. Well, it would come in and the hub would get it and everybody in this side of the network would get it. They'd be bothered by it, and this guy would receive it. Everybody else would drop it. But the bridge would get that and say, oh, well, I've learned that the MAC address that you're communicating with belongs on this side of the network. It's located over here on the left. So I will not send that message over to the right side of the network, and everybody on the right side of the network is no longer bothered by those messages that are coming through. You've essentially split your network in half. Now, that was probably, bridges were really popular in about the mid 80s, early 90s timeframe as a solution to help split up our network or divide our network, because bridges could have multiple ports. It could have, another connection up here to another hub and another hub down here, but they typically had a very limited number of ports. The other problem with bridges is they were very slow. As they learned MAC addresses and forward traffic, they had to look them up, and it was all software based, meaning there's a program installed on side of that bridge that would have to look up the MAC addresses. And it would kind of slow down the network communication, at least compared to a hub, but it was better than having collisions left and right. So that was where the final solution came out, our switches. Switches, first off, split each port into its own collision domain. This is why I nearly had a heart attack at the retail store that shall remain nameless when the guy said, oh, there's no real difference between a hub and a switch, and, other than the cosmetics of them. Well, there's a world of difference, because a switch has every single port as its own collision domain, meaning every single device that's plugged into its switch can send at exactly the same time, and you won't have any problem at all. Essentially, when you get rid of all the hubs in your network and replace them with switches, you will have no more collisions, unless there's some kind of major network problem. You will have no collisions at all, and it completely clears up network communication. Second benefit of moving over to a switch is, since each port is split into its own collision domain, it now opens the door to something known as full duplex communication, meaning instead of saying our devices will send or receive, they can now send and receive. I don't know if you knew it, but when you bought a network card that is rated at 100 megabits per second for your PC, you are at no extra cost getting a network card that can actually do 200 megabits per second, because all network devices are rated in half duplex, meaning they're rated as send or receive at once. But when we have a full duplex communication or network card turned on, we can actually receive 100 megabits per second, and we can send 100 megabits per second at the same exact time. That's the benefit of full duplex communication. One more benefit of switches is that they now moved all the MAC address learning. You know what bridges were very slow at because they were software based? They moved it into a hardware chip. It's actually known as an ASIC. Now, you won't need to memorize that and know what that is, but you'll hear the term a lot when you're looking at switch statistics. They'll say, yeah, we use ASICs, which stands for Application Specific Integrated Circuitry. It was actually a chip that was created by IBM, which moved all the intelligence of the bridge, which required a software program to run, into hardware. The result is that a switch can move data just as fast as a hub can, which everybody says is wire speed. As fast as the wire can transmit, as fast as your data can get from that computer to the switch, is as fast as it can move it over to the other side. Speed of electricity, speed of light, you could say. So switches have become very fast in just about every network environment. Well, I don't want to generalize, but I'll say most network environments have replaced all of their hubs with switches because the cost of them have come down quite a bit in recent years. All right, last thing we'll talk about as we wrap up this video is how a switch does what it does. How does a switch switch? Well, when you first pull a switch out of the box and you plug it in and you boot it up and you plug all your PCs into it, it has this thing in memory known as a CAM table. Now let me back up a little bit. A switch is said to work at the data link layer of the OSI model because it can see MAC addresses and it can learn them. A hub is said to work at the physical layer of the OSI model because it just sends signals. It doesn't look at MAC addresses at all. It just regenerates electricity and sends it out a port. So when this switch first boots up, it has this thing known as a CAM table. Now, if you're an acronym junkie like me, that stands for Content Accessible Memory. It doesn't really mean anything other than it's a place in memory that it can store MAC addresses. But when it first boots up, it's in memory, RAM. It's clear, it doesn't know anything. So traffic actually has to be sent before the switch can become intelligent. Now let's say computer A up here wanted to communicate with computer B. The first thing it's going to do is, B will have its IP address. A is going to need to know what MAC address it is. So it will send what kind of packet? An ARP, Address Resolution Protocol. It's a broadcast that says, hello, I need to know the MAC address of PCB. Now, an ARP is a broadcast message. And remember, a switch is no different than a hub on that. It's only one broadcast domain, so one broadcast will go everywhere. So all PCs will get that broadcast saying, hello, I'm looking for the MAC address of PCB. But stop right there. Inside of that ARP message is a source MAC address of PCA so that PCB and all the PCs will know who generated that ARP request, and it will be a destination MAC address of a broadcast. Technically, if you open a packet sniffer, which we'll do in a little bit, you'll see the destination MAC address for a broadcast is all Fs. In hexadecimal, it's everything turned on, all Fs. But when it saw the source MAC address come in port 1 of PCA, this MAC address right there, the switch suddenly became smarter. Boing. Port 1, it said, aha, I've learned who you are, PCA. I've seen that the MAC address 00A0121113321 is located out my port number 1 right here. The switch just became one MAC address more intelligent. Now, PCB gets that broadcast and says, oh, they're looking for me. So it responds back and says, hey, PCA, here is my MAC address. Suddenly, boing, the switch became one MAC address smarter because it knows now where PCB is located. It remembers port 2. Now, it still doesn't know who PCC or PCD are because it hasn't learned their MAC address yet. So if PCA, here's a good certification exam question for you. If PCA somehow knew the MAC address of PCD and said, hey, I'm going to send from a source of me and to a destination of PCD down there, that message will come into the switch. And the switch, since it doesn't know where PCD is, will treat it like a broadcast and send it out all ports except the port it received it on. So PCD will get the message, but it won't be until PCD or PCC respond to that the switch will learn their MAC address and start becoming more and more intelligent. Truth be told, when you boot up a switch, it will probably take that switch 30 seconds. I would even say that's conservative. 15 seconds or less to learn every MAC address of every device that's plugged into it. Because computers are chatty. They're always sending stuff and receiving stuff. So it won't take the switch long to build that MAC address table. And from then on out, when PCA wants to send to PCB, all the switch has to do is take that message in, look at its CAM table, look at its MAC address table, and say, oh, you're just going out here. And it does not disturb any of the devices on the network. This is why this switch is considered to have 4 collision domains. It's separate, it isolates them. Only the traffic that belongs out each port will go out it. That should give you a good idea of the difference between a switch and a hub, and also tie together that concept of collision domains, which is how many people can send at the same time, and broadcast domains. That's what solved, these switches are what solved the problem with CSMA CD by splitting our network up to where every device can send and receive at the same time. Last thing we talked about here was how a switch switches, how the switch becomes more intelligent learning those MAC addresses. Frankly, I'm really excited because we're about to make the transition. This video marks the transition or the end of the major network concepts, and we're going to start the next video into getting into configuration. So for now, I hope this has been informative for you, and I'd like to thank you for viewing, and I sure hope you go right in to that next video.